to thank Dr. de Grey and his staff for inviting us to speak. It's truly an honor for myself as well as CR Sciences to share some of the work we've done. And I have to thank Jerry Shea for actually providing most of the introduction that I was going to provide for you today. So I'll be able to breeze through some of the slides and maybe spend a little bit more time on some of our data. So this is a picture of Woody Brown. He's 95 years old and still surfing in Hawaii. Wouldn't we all like to age as well as he has? But when we talk about life extension, of course, and we've already spoken about this here and last night, it's not just about living longer, it's also about having increased health span. And so we have to consider that, and as Jerry pointed out to us, that anything or almost anything that we're going to do to extend the lifespan of our normal cells is potentially also going to expand the lifespan of our cancer cells. And so that's something that we're absolutely going to have to deal with, and we recognize that. And so based on that, I want to take a short tangent. It's going to be a lot shorter than it would have been if I hadn't been going after Dr. Shea, but to talk about cancer just a little bit and how it relates to aging and telomeres. And Jerry already pointed out that anything that then decreases cell proliferation potentially then is a tumor suppressor pathway. And replicated senescence or telomere shortening is known to then be like a cellular clock that stops cell proliferation once the telomeres get to a critically short length. So we're still going to have to deal with the idea, as I said previously, that increasing telomerase or turning on telomerase in an effort to lengthen telomeres is going to then bring us back to the cancer issue. And actually the cells we're interested in are these cells that really aren't cancer yet, right? They're actually maybe not even precancerous cells, but they're cells that have lacked growth control. Somewhere along the line they've acquired a mutation that's allowed them to bypass cell cycle regulators. And then if we think about the historical timeline of cancer, then eventually, as these cells continue to divide, their telomeres get shorter and shorter, and as Jerry showed, the M1 and M2 crisis, eventually they're going to become immortal, either through induction of telomerase activity or the ULT pathway. When we're talking about extending lifespan and finding ways to turn on telomerase, we're not really interested in these cells. It's a little bit too late. In these cells now we're into curing cancer. We're into fixing things that went wrong. It's actually these cells that we're most concerned with in our field of telomerase activation. We don't really have a good name for these cells, and we found this interesting. We've asked people, what are these cells? What do we really call these cells? And we haven't really found a good answer, but they're critically important to anybody that's trying to extend lifespan. And another big question that needs to be answered is actually how prevalent are these cells? Is there a whole lot of them? Is there just a few? And so we're going to have to develop means to not only identify these cells, but then deal with them as we're attempting to extend lifespan. So as a little segue into what I'm going to talk about, what are some of the solutions then for life extension? And we've heard a little bit last night about Dr. de Grey's theory, his SINS theory, and this is just a portion of it. But one thing we could do is delete HTERT as well as the ULT pathway. This would then stop the cancer cells. What would happen in addition, though, as Dr. Shea pointed out to us, is we delete the HTERT gene and the ULT pathway in this case, but I'm talking about the telomerase gene, our telomeres of our stem cells are going to get shorter and shorter and shorter. So we're going to have to deal with that issue, and one way to deal with that would be then to infuse the body with stem cells on a regular basis then that actually have these pathways knocked out. This is a very elegant way, and it's just a portion of the SINS idea. But we would like, and we are always thinking of things that aging, as Jerry said, is a hugely complicated process. And there's probably going to be multiple facets that are going to have to come together for us to actually cure aging. And so parallel efforts, then we would suggest we would cure aging, not necessarily our company, the community, cure aging without inhibiting telomerase. Then, once we get to that point, then we turn telomerase on. We would suggest too, and we often talk, that telomerase induction in a transient environment. So it wouldn't be turned on all the time, but a small molecule that we could take that could turn it on for, let's say, a few months, extend the telomeres, and then be taken away would be a much safer method than actually having telomerase turned on all the time in the cell. And telomerase may not be such a bad thing, and Dr. Shea pointed out a lot of important points about telomerase, because we do know that there's quite a bit of evidence that telomerase will actually decrease the risk of cancer. And we'll hear more information in this area as the conference goes on. One thing that we're pretty confident about is bad things happen when telomeres get short. Understanding the cause and effect relationships there is something that we still need a lot of work on. And as Dr. Shea showed you, that in cells and cell culture anyway, preventing telomere shortening will extend the health span and lifespan of cells and culture. Unfortunately, we don't know if that's going to apply to humans. Okay, can we extrapolate what we know about cell culture to humans is a question that hasn't been answered yet. And that's the fundamental question that Sierra Sciences is attempting to answer. We'd love to get to this point and answer this question. And there's a number of diseases that could be helped by the prevention of telomere shortening. So with that, I'm going to now start on what I came here to talk about, which are to discuss some of the tools that we're using to help us in the struggle to keep our telomeres long. Sierra Sciences has been in existence for about 9 years, and we've worked really, really hard trying to figure out all we can about telomerase. We've spent quite a few years doing a whole bunch of telomere promoter analysis, bashing. We'll have a couple posters. For those of you who are interested in our work, we have like 10 or 11 posters over the next couple days. And so we'll be showing a lot of what we've been doing. We have a couple that then kind of show what we've done trying to understand regulation of the telomerase promoter. We spent a couple years trying to find the proteins, transcription factors that actually bind to the telomerase promoter in areas we believe is involved with regulation. And through these efforts then, on the side, we were always taking anything we saw in the literature, any small molecules, any processes, anything that anyone had put out there, and asked ourselves, is this the answer to our question? And unfortunately, we were not able to reproduce any of the work that is in any of the published documents. We can make a lot of HDAC inhibitors work in a transient transfection assay. For instance, using the telomerase mineral promoter driving expression of a reporter, and HDAC inhibitors work very well to induce activity of the telomerase promoter in that context. But in terms of the endogenous promoter, we haven't been able to do it. That really set us back. If you think about a company that's working with normal cells, trying to discover how to turn something on that's turned off, and you set up as best controlled experiments as you can imagine, and what does a negative answer tell you? Not necessarily a whole lot. And then a lot of people, we have a lot of collaborators, and they'd say, well, how do you know that normal cell is even telomerase competent? Maybe telomerase has been turned off so long that you're never going to be able to turn it on. And then even if you turn on the message, how do you know that cell's capable of then processing it correctly and ending up in actually active protein? And so we are very diligent, but we don't take no for an answer, and so we've struggled with this for a long time. We now have been doing a lot of screening. We have a 300,000 compound library, and we have various screens, and we're searching for compounds that will turn on telomerase. And this is the result of one of our screens. May not look like much, but what we're seeing here is it's actually RT-PCR for H-chart message, but you don't have to turn this on. And you see here along the x-axis a series of numbers. These are representing compounds from our compound library. And then the blue bars are actually GAP-DH, so they're basically our control for the system. We have MRC5, which is a human fetal lung fibroblast cell line that's ectopically expressing telomerase, and you can see we get a whole bunch of message. The y-axis is showing raw CT values. If you're not familiar with RT-PCR, basically CT is critical threshold. And so the more message you have in your sample, the more quickly you'll pass a critical threshold. So in this case, we're looking for lower numbers. The lower the number, as I go here, we've made this backwards, the lower the number, the more message we have. But what really got us excited was this little blip right here. Doesn't look like much, does it? And actually, we've been teased so many times that we were only cautiously optimistic, and we're not. We repeated it a bunch of times, of course, and saw this same thing happen over and over again. Well, so here we've demonstrated a compound that's capable then of inducing telomerase message. We haven't shown that we've actually have active protein yet. In order to assay for active telomerase protein, we do a trap assay, and Dr. Shea did show some trap gel, so I'm going to go through this pretty quickly. The telomerase assay is based on the idea that we can use an artificial telomere. If telomerase is in the sample, then it will extend the telomeres. And then the telomerase complex is there, representing the protein component and the RNA component. And telomerase then adds telomeric repeat regions, or 6 bases at a time, successively onto the end of the telomere. If you run this product on a gel electrophoresis gel, then what you end up seeing is a ladder that represents PCR fragments, telomerase created and then amplified by PCR, that are 6 base pairs in differences in length. And so here in this particular gel, we're seeing HeLa, which is a cancer cell line. And then we usually put 100% HeLa, 5% HeLa on our gels. 100% just means we had 100,000 HeLa cells. 5% means we had 5 HeLa cells and 95 normal cells that were lysed. And so we use it kind of as a quantitative effort. Okay? And then here we see MRC5 cells that are negative for telomerase. When we expose these cells to our compound, which I guess I forgot to say here, so I'm going to back up just because I can. This is our 57,684th compound in our library. So the 57,684th compound we tested, we finally saw a little blip. And we call this compound C0057684. Okay, so I'm going to refer to it now, and because it's C0057684 is a mouthful, I'm going to say 57684. It's just to clarify that. Sorry about that. Okay, when we exposed normal cells to 57684, and this is an experiment done in triplicate. This is the first time we've ever seen something actually turn on telomerase activity in a normal cell. Huge breakthrough for our company. It validated what we've been doing all along. It validated all of our screens, and so it's really, really, really important for our company. So what I want to do now is show you some of the work, and we haven't done a lot. It's fairly new, relatively speaking. Some of the work that we've done investigating this compound. We've done some dose curves. It is dose responsive. Again, here we have this is mRNA relative to HeLa. Everybody seems to know HeLa and telomerase, so we've pretty much done that. Across the x-axis, you see increasing concentrations of 57684, and you can see a concentration-dependent increase in telomerase message. When we then run trap assays, and I've truncated the work here, I've started with just the 15 micromolar, and you can see we start to see a hint, and then increasing amounts. We've looked at a time course to say how quickly does it turn on. And so here we've added the compound to normal cells and then assayed for telomerase activity various hours later. And you can see that it starting to see in 12 hours, you can see at 24, peaks at 48. When we go out to 96 hours, we've pretty much lost the activity. We've also done some extinction work where we look to see how long telomerase hangs around after we remove the compound. And here you can see 8 hours, 16 hours, 32 hours, 48 hours after we've removed the compound, we're seeing a significant reduction in telomerase activity, and then eventually it completely disappears. We've tested this in other cell lines. Maybe it was a fluke, right? We had a cell line that was telomerase competent. These are two other fetal lung fibroblasts, MRC9 as well as IMR90. They both respond to the compound. We've tried foreskin fibroblasts, BJ, as well as CCD1114. Again, they respond to the compound. We've looked at keratinocytes, and this is a phenomenon that we have seen in other cell lines too. So you can see here, these are adult human keratinocytes. These are neonatal keratinocytes, and the neonatal or the younger cells seem to respond more strongly to the compound than older cells. And then here we've looked at BJ cells at PDL or population doubling length 28 and compared it to 53. And we see that older cells also, they do respond, they do not respond as strongly as young cells. We've also looked at some confluent versus non-confluent cells and see a similar phenomenon. So it seems to suggest that for this compound to work, the cells need to be actively dividing. Okay. Because we were unable to repeat other labs' work on so many occasions, we felt really, really strongly that we would in no way say we had a compound that really worked until we had independent verification. And we were fortunate enough to have Jerry Shea's lab, Jerry Shea and Woody Wright's lab test it for us, and they've been able to repeat the results in different cell lines. Judy Campisi has also repeated it for us, and Richard Alsop at the University of Hawaii. We're really thankful for their participation in this effort, and now we feel pretty confident that we can say that 57684 does induce H-short expression. Another compound that we've had the privilege to work with, and it's a nutraceutical, is a compound called TA65. TA65 is derived from the astragalus root. It's a compound that was originally identified by Geron Corporation, and it's now being commercially distributed by TA Sciences. And Noel Patton is here in the audience from TA Sciences. So if anyone has any questions, then he's here, I think, for the duration of the conference. So when we looked at TA65, and this is in keratinocytes, and you can see here we have... this is MRC5, not keratinocytes. We've done it in keratinocytes as well with similar response. And MRC5, median DMSO, we don't see any activity. And then you can see, albeit not strong, but absolutely there, telomerase activity in response to TA65. This is a repeat of the same experiment, again showing that we see activity as a result of this compound, and then an additional experiment. So we now have two tools, two compounds that we can use that seem to act a little bit differently too. They're not as concentration, TA65 is not as concentration responsive as 57684, and seems to express telomerase at maybe a little bit lower levels. Okay. So we've taken these now and asked ourselves the question, what about immortal cells? And we've looked at some alt cell lines. Here's 3 of the alt cell lines we looked at, and all 3 respond to 57684 with increased message. TRAP is a little bit tricky with these cells. It's kind of a mess right now, and we're still working on that, trying to figure out exactly how to do TRAP on these cells. We've looked at HeLa cells, and this we were really quite surprised about. In this case, our y-axis is actually showing DMSO set to 1. So this is relative. So because HeLa is a telomerase positive cell, actually we've got a bunch, so we set that equal to 1. But TA65 doesn't seem to affect cancer cells. Probably good news. for those taking TA65. But 57684 results in approximately a 20-fold increase in message in response to the compound. We've done trap assays then on HeLa cells, and you can see 50% and 10% HeLa relative to the 57684. And it's not only increasing message, but it's increasing active telomerase complex. We've looked at a few other telomerase positive cell lines. In most cases, we see increases in expression. I'm sorry I didn't put the number for HeLa on there. I was supposed to, and I didn't. This is actually, all this information is going to be in posters, so if you want to look at a better slide that actually has all the data on it, it'll be at our poster session. But this is going up into the 2000s, so we truncated it so this looks more important. Interestingly enough, NTERA2, which is a cancer stem cell line, is not responding to 57684. Okay. So maybe the downside of 57684. One thing that we notice over and over again is it is mildly cytotoxic. So these are a microscopy. Obviously, you see before treatment the cells, and then 48 hours after treatment with DMSO, we see confluent image. But we can see here that with 57684, we really haven't had a lot of cell growth. We don't see dead cells floating, and this is typical. We just see reduced number of cells. And this is concentration dependent. And so here you see before and then zero concentration. And when we go along, we start to see a little bit of reduction in cell growth here. 15, we can obviously see reduction in cell growth. And 30 and 60. So we are seeing some effects on cell proliferation. We wondered if these cells were actually alive or not, or are they just, still sitting there, but they're dying. And so we did some live dead cell assays. So in this particular image, we see light microscopy. Here we're staining with calcin AM as well as amphibian hemodimer 1. So at the same time, dual staining, and we've used a Texas Red FIDC dual filter. So if they're, and red cells signify dead cells, and green cells are live cells, and you can see here we see all green cells, no red cells. So it looks like we aren't killing the cells. And one thing we also know, and you'll see some CPD studies in a minute, that when we take the compound away, the cells recover and start to grow again. TA65, on the other hand, is not toxic at all to the cells at these concentrations. It's an important point. Okay, when we looked at some other toxicity indicators, in this case this is measuring ATP levels using a luciferase assay, and we can see with concentration, these are fibroblast cell lines, so they're normal cells, MRC5 as well as BJ skin cells, and we see a reduction in ATP levels with an increase in concentration. I don't know if this is really representing any toxic effects on metabolism, because remember we have less cells in these at these higher concentrations as well. So I don't think it's reflecting effects in metabolism. I think it's reflecting effects in cell number. Interesting enough, when we look at cancer cells, we see a much stronger response. I don't have microscopic images, but cancer cells, we do see floating cells. They're much more sensitive to the compound, and we see cell death. And so you can see here we see marked decreases. The blue is SAOS2, which is an alt cell line, and HeLa, a telomerase positive cell line, and we see significant decreases. Okay. Of course, as soon as we showed this data to a number of people, particularly Dr. Shea, he said, oh, it must be a DNA damage response. And indeed, maybe it may well be. We don't really have a clear answer to this. We have things in progress. Dr. Shea's lab did do some preliminary work on gamma H2AX, although it wasn't very large scale and the results were inconclusive, so we don't really have the information there. We have tried to look at AP sites using some kits, and we're still kind of working that out because didn't quite work like we wanted to at first, so that's still in progress. But one thing that we did ask ourselves is, we've never really seen in the literature any proof that DNA damaging agents actually turn on telomerase. There's what we would call circumstantial evidence, but nowhere did we find trap assays where we saw increases in telomerase activity. So we stopped and asked ourselves then, will a DNA damaging agent actually turn on telomerase? And we've used etoposide here. We're actually using a handful of compounds right now in the lab to study this. Etoposide is a widely recognized DNA damaging agent, and we asked ourselves, does it turn on telomerase? And here you can see messenger RNA, H-TERT message relative to HeLa, DMSO, and we compared 57684 to etoposide at two concentrations, 10 and 30 micromolar. 10 micromolar seems to be the concentration that's most widely used in the literature for studying etoposide as a DNA damaging agent. And you can see that we do see some increase in message with the etoposide. When we bump it up to 30 micromolar, it doesn't seem to be as responsive, although 57684 does increase much more than the etoposide. We've hypothesized that maybe the answer to this is the fact that 30 micromolar etoposide is really toxic to the cells, and so most of these cells are dying. And so we need to do some further explorations to further investigate those results. We get really excited when we see a compound, so we can hit it with everything we've got. So we've done some DNA array analysis on these compounds. And maybe another unfortunate result for 57684 is it just is affecting a tremendous amount of genes. And way too many for us to be thinking that this is the compound, this is it, that we've actually found. You can see 1,700 of the genes have been upregulated twofold or more. I know this is fold expression of the DMSO, it's actually twofold or more. So we have a significant number of genes. We're still in the process of analyzing these. We got some preliminary results. We have about 3 different companies looking at this for us. It seems so far that the vast majority of these, or the most significant genes affected, are cell cycle control genes, which probably doesn't surprise anybody. There is some DNA damaging or DNA damage response genes that are upregulated, but they're at much lower levels. But we're still investigating this. Ts65, on the other hand, is not showing these kind of results. It seems to be very specific, and it's only increasing a handful of genes. Okay. We've done some extension of lifespan studies. It's probably premature a little bit for this, especially given the fact that the compound affects cell proliferation rates, but we've done them anyways. And so you can see here that when we continuously expose cells, normal cells, to the compound, and this is DMSO showing basically a normal growth curve there. You can see at all concentrations that we've tested, we basically are just we're not allowing the cells to grow. Conversely, when we did a 96-hour treatment and then took it away and then followed these cells over time, here's DMSO in the black and a series of different concentrations of 57684, and we see a very modest increase in cell proliferation. It's, like I said, PDLs, population doublings. Really not much to write home about at this point. We're continuing these studies. We have a lot of different scenarios we're working out, and we'll see if we can get something going on a little bit better. We're also currently investigating Ts65 for its ability to increase cell proliferation rates. So what's next for us, and that seemed to find 2 more minutes, is that we're actually focusing on screening more than we're focusing on characterizing 57684. And we have posters that are outlining the different screens that we're doing. We're going to look at other cell types. We're interested in synergy, maybe Ts65 and 57684 mixture, or maybe HDAC inhibitors with 57684. See if we can loosen up the chromatin a little bit. We've been working on some mechanisms of action and structural activity relationships an attempt to develop more active or less toxic compounds, and then, of course, replicated lifespans. I'm going to skip through because these we actually have as posters, our different screens, but I do want to show you this. Here is RT-PCR of normal cells, and here we have analogs of 5768. Here's 57684 Genoso. These are various analogs of 57684. We have about 15 or 16 in our compound library right now. And you can see that some of the analogs result in a response while others do not. And so we have an opportunity to look at structure-activity relationships based on this. And when we do trap, we see a similar, it follows the message really quickly, so we continue to screen. I want to say that these tools are freely available. We are a small company and have an enormous amount of work to do, so we're really interested in collaborations. We're looking for researchers not only as collaborators, but also for people interested in coming to work for us. And if you have any interest in that, please talk to myself or some of the other CR Sciences people. Come to our poster sessions. And then I wanted to acknowledge a few people, CR Sciences staff. We have an awesome staff. Actually, there isn't any one person that does everything. It's just a huge collaborative effort. I wanted to focus or acknowledge Lancer Brown, who orchestrated the RT-PCR work, and Jessica Wheeler, our cell culture manager, who then would make sure all the cell culture gets done and all of the trap assays. And so we have a couple other people, Jerry Shea, Judy Campese, and Richard Alsop, for helping us with a number of projects. Jerry and Woody and Judy are also on our scientific advisory board. Federico Gaeta is also on our scientific advisory board. He's also our chemist. So if you have any questions about the compound or structure activity, he'd be the person to talk to, and he's here. Bryant Viaponto is also on our scientific advisory board. Brian and Fed both also worked at Geron Corporation, and Bryant will be presenting a poster this weekend. Joe Hedgepath is on our scientific advisory board. TA Sciences and Calvin Harley for the opportunity to work with TA 65. Thank you so much. And the University of Nevada. Thank you.